Beneath Tokyo Station, a century-old brick building is supported above a hidden seismic isolation layer. Approximately 350 isolators and 160 oil dampers reduce how directly ground motion reaches the structure above. Across the city, a 634-meter tower hides a second spine, a concrete column built to sway out of sync with it. One skyscraper carries an approximately 1,800-ton moving mass on its roof, built only to fight the building's own motion. Bullet trains break before the strongest shaking arrives. Gas lines cut themselves into blocks mid-earthquake. Bridges are restrained to their own supports, so the deck cannot slide off. And on the coast, one nuclear plant took extreme shaking that exceeded parts of its design basis, then a tsunami, and still reached shutdown. None of this is one technology. So when the first defense is exceeded, what takes over next? Retention contract. This is how failure moves through a modern city. First, controlled movement beneath a historic building. Then, two structural systems oscillating at different periods. A rooftop mass reduces long-period sway. Trains break after the first weak vibration. Gas networks isolate damaged blocks. Bridge restraints prevent complete unseating. And at Onagawa, multiple independent defenses had to remain available after individual components were damaged. Each chapter asks the same question. When one layer reaches its limit, which layer still remains available after another has failed? This isn't a celebration of earthquake-proof buildings. Nothing here is invulnerable, and no engineer in Japan would claim otherwise. This is an investigation into layered failure control, letting some things move, forcing others to stop, and protecting only what matters most. It starts underground, beneath a station most people only ever pass through. Chapter 1. Tokyo Station, the building detached from the ground. This is the Marunouchi side of Tokyo Station. Red brick, twin domes, a facade restored to the form of its original 1914 design. The building survived Tokyo's 1923 earthquake, still standing. Decades later, it lost its roof and much of its interior to wartime firebombing, then spent 60 years patched over rather than restored. What it could not survive indefinitely was staying exactly as originally built. By the early 2000s, engineers faced a specific problem: protect a nationally important cultural property, still one of the largest terminals in the country, without closing it, and without changing a single visible detail of its exterior. So they went underneath it. The original building had stood on roughly 11,000 pine piles driven into the ground when it was built. Engineers now had to remove them one by one, temporarily supporting the existing structure on new piles and steel beams, while excavating 2 full basement levels beneath a station still crossed by thousands of commuters a day. Every one of those old piles had to be located, extracted, and replaced without ever letting the historic structure above lose its footing, even for a moment. The work went on for years, mostly out of sight below street level, while trains kept running on schedule overhead. In their place, approximately 350 seismic isolators and roughly 160 oil dampers. Layered rubber and steel bearings allow controlled horizontal movement relative to the ground below. From the outside, none of it is visible. No crack in the brickwork, no seam in the plaza paving gives away what's happening in the layer underneath. Not stiffened into rigidity, allowed to move within the range the isolation system was designed to control.
Japanese engineers generally describe 3 strategies for surviving an earthquake:
Taishin, resist, relying on strength alone. Seishin, dampen, absorbing energy somewhere inside the structure. Menshin, isolate, reducing how much ground motion transfers into the building at all. Tokyo Station is Menshin, base isolation, retrofitted onto a building already 90 years old when the work began. During an earthquake, the isolation layer reduces and lengthens the horizontal motion transmitted into the historic structure, while the oil dampers dissipate part of the energy. This is not a building floating free of the earth. It still stands on real supports, still carries its own weight. What changed is what happens the instant the ground moves horizontally. Millions of passengers now pass beneath the domes every year with no idea that a hidden layer beneath their feet decides how the whole structure will move the next time the ground shakes. The restoration finished in 2012. The completed restoration returned the Marunouchi building to the appearance of its original 1914 design. That's the point. The history stayed on the surface. The engineering moved underground, where no tourist photograph will ever show it. But Menshin solves only one stage of the problem, the ground shaking directly beneath a relatively low structure. It says nothing about a building that has to survive its own height. 600 meters of steel, deciding in real time how to argue with itself. Chapter 2. Tokyo Skytree, the tower with a second spine. At 634 meters, Tokyo Skytree turns height itself into an engineering problem. Its predecessor as the city's tallest structure, Tokyo Tower, stood 333 meters. Skytree rises almost twice as high, which meant the old rulebook for keeping towers stable in an earthquake no longer applied cleanly. Skytree is a freestanding broadcast tower first, built to keep transmitting television and radio signals across the region, even while it moves. The taller a structure is, the more its upper section can whip back and forth once an earthquake reaches it, a motion that gets worse, not better, the further up you go. Skytree also has to survive something Tokyo Station never has to consider: hours of continuous typhoon wind pressing against the same structure, not seconds of ground shaking. One system had to answer both. Running through the tower's core is a reinforced concrete column 8 meters wide and 375 meters tall. Engineers call it the Shinbashira, the central pillar, a name borrowed cautiously from the pillar found at the core of Japan's traditional 5-story pagodas. Skytree's designers didn't copy that older design. They studied the underlying principle and rebuilt it in concrete and steel at a scale no pagoda ever attempted. Up to 125 meters, the Shinbashira is rigidly tied to the tower's steel frame. Above that height, the connection changes completely. The column links to the outer lattice only through dampers, devices that allow the two structures to move at different speeds instead of as one. Inside that concrete spine, hidden from public view, runs one of the tower's emergency staircases. The concrete core is heavier. It sways slowly. The steel lattice is lighter. It sways faster. The relative movement between the heavier concrete core and the lighter steel frame allows the damping system to substantially reduce the tower's response, whether the force pushing on it comes from an earthquake or a typhoon. This is not base isolation. The tower isn't sitting on rubber bearings the way Tokyo Station now does. It's something else entirely. Two massive structures built to disagree with each other on purpose every time the tower is pushed. That disagreement doesn't make the tower indestructible. It changes how far the top can move. It does not decide whether the structure can be damaged at all. Tokyo Station changed the motion before it ever reached the building. Skytree lets the motion in, then fights it once it's already inside. But tall office buildings face another problem: long period motion that can continue after the strongest local shaking has faded. Chapter 3. Shinjuku Mitsui Building, the 1,800-ton pendulum on the roof. Completed in 1974, the Shinjuku Mitsui Building was built to the seismic standards of its era. 55 floors, structural steel, sound by every code that applied to it at the time. Then came 2011. The Great East Japan earthquake struck far offshore, hundreds of kilometers from Tokyo. But its energy didn't stay near the epicenter. It produced long-period ground motion, slow, rolling waves capable of traveling enormous distances with very little loss of strength. Tall buildings can be especially sensitive to long-period motion. When the period of the ground motion approaches a tower's natural period, movement can build through resonance. Across Tokyo and Osaka, high-rises kept swaying for minutes after the shaking near their foundations had already stopped. Elevators halted mid-shaft. Furniture slid across floors. People on upper levels describe the sensation as closer to seasickness than an earthquake.
At the Shinjuku Mitsui Building, the issue was not failure to meet structural requirements. The problem was that a compliant tower could still sway long enough to disrupt occupants, equipment, elevators, and business operations. By April 2015, engineers had retrofitted the Shinjuku Mitsui Building's roof with 6 pendulum-style masses, 300 tons each, 1,800 tons combined, tuned to swing opposite to the tower's own motion.
At the time, it was described as the largest tuned mass damper system of its kind in Japan. 6 separate masses arranged symmetrically around the rooftop so the building would respond evenly no matter which direction the sway came from. When the building sways one direction, the mass lags behind, then swings the other way, canceling out a share of the movement before it can fully build. The system needs no power source at all. It works purely on pendulum physics, the length of the cables and the weight of the mass tuned to match the building's own natural rhythm, which means it keeps functioning even if the building loses electricity entirely. This is not a structural reinforcement. The building never needed one. It already met the safety requirements of its own era. It is a retrofit addressing long-period motion that was not the central focus of the building's original design. How long a structurally safe building can keep moving, and what that motion does to the people and equipment still inside it. The pendulum does not stop the tower from moving. It significantly reduces both the amplitude of the sway and the time required for that motion to settle. Structural safety and usability turned out to be 2 different problems, solved by 2 different technologies 4 decades apart. That distinction becomes critical for anything that has to keep operating the moment the ground stops, like a train already moving at 320 kilometers an hour. Chapter 4. Shinkansen, the train that breaks before the strongest wave. An earthquake doesn't arrive all at once. It sends 2 distinct kinds of waves outward from its source. The first, called a P wave, travels fast and shakes weakly, a tremor most people barely register. Stronger seismic motion generally follows the first weak P wave signal. Between those 2 arrivals sits a gap, sometimes only a few seconds, sometimes longer, depending on distance from the epicenter. JR East's Shinkansen network exists to exploit that gap. Seismometers positioned along the tracks and offshore on the seabed detect the P wave the instant it registers.
The system estimates the likely magnitude and location within seconds, then automatically cuts power to the overhead line and triggers emergency braking without waiting for a human decision. In late 2023, JR East and Japan's Railway Technical Research Institute refined exactly how the system estimates magnitude from that first weak P-wave signal. The upgrade, rolled out across JR East's Shinkansen seismometers in March 2024, cut the average time between detection and power cutoff from about 3.9 seconds to about 1.3 seconds. 2.5 seconds doesn't sound like much. At 320 kilometers per hour, braking can begin roughly 230 meters earlier. This is not earthquake prediction. Nothing in this system knows a quake is coming before it starts. It exploits a physical head start, the seconds between a wave that only warns and a wave that actually damages. It also isn't a guarantee. If the ground beneath a section of track fails outright, or shaking is severe enough at close range, derailment remains possible. In 2004, a Shinkansen derailed during an earthquake in Niigata Prefecture for the first time in the service's history. The train was too close to the epicenter for the system to stop it in time. It came at the rails at roughly 200 kilometers an hour and stayed upright. None of the passengers on board were injured. That outcome is part of why Shinkansen cars also carry L-shaped guide devices engineered to limit how far a derailed car can move sideways off the rail, a second layer in case the seconds run out entirely. Seconds bought here don't just protect a single train. They buy time for every the earthquake reaches next, starting with the gas lines running beneath the city that train just left. Chapter 5. Tokyo Gas, the network that cuts itself into blocks. A ruptured gas line is not a hypothetical risk after an earthquake. It's one of the most consistent causes of fire in the hours that follow, feeding flame into a city already full of collapsed structures and severed power. Tokyo Gas's answer starts inside individual homes. Microcomputer meters deployed across the service area are designed to shut off gas automatically when strong shaking is detected, specifically an intensity of 5 or higher on Japan scale, with no signal required from anywhere else in the system. That's the first layer. The second operates across the entire city. The company began dividing its supply area into isolated blocks back in the 1980s, once it was designated a public institution under Japan's disaster management law, the status that comes with a legal obligation to maintain exactly this kind of emergency response capability. The earliest version of that network split the city into roughly 100 blocks. After the 1995 Kobe earthquake, which showed in brutal detail how fast gas wires spread through a damaged city, Tokyo Gas expanded and hardened the system further. Today, the pipeline network is divided into more than 300 low-pressure blocks and roughly 25 medium-pressure blocks, all monitored through a real-time system called Supreme. Seismometers spread across the service area, feeding data back to a central control center as an earthquake unfolds. When an earthquake strikes, the control center doesn't shut off gas to the entire city. It identifies which specific blocks show signs of serious structural damage, then cuts supply only to those, remotely, without sending a technician into the field first to confirm anything. The pipes themselves changed too. Much of the old low-pressure network was gray cast iron, rigid, prone to fracturing under ground movement. Most of it has since been replaced with flexible polyethylene, a material that flexes under stress instead of cracking outright. Low-pressure pipe makes up roughly 90% of the entire network's length, which is exactly why the material of that specific layer matters so much. None of this eliminates risk entirely. A ruptured pipe near open flame is still dangerous,
And restoring gas service to a damaged block afterward remains its own slow, careful process, done street by street. Even at the household level, restoration isn't automatic. Most microcomputer meters require a manual reset once it's safe. A small, deliberate safeguard against restarting supply into a line nobody has actually checked. What the network optimizes for isn't zero risk, it's containment, keeping damage local instead of letting it become citywide. But knowing exactly where the gas supply is safe means nothing if the roads needed to reach the damage don't survive the same earthquake.
Chapter 6: Japan's Retrofitted Bridges. The roads rebuilt not to fall. No single event reshaped Japanese bridge engineering as sharply as one morning in January 1995. The Great Hanshin Awaji earthquake tore through Kobe and brought down sections of elevated highway that had been considered structurally sound the day before. Some spans didn't just crack. They toppled sideways, their decks sliding completely off the piers that had carried them for decades. A collapsed bridge deck isn't only a piece of damaged infrastructure. It's a route that no longer exists exactly when it's needed most. Ambulances, fire crews, and supply convoys depend on those same elevated routes. If the route disappears, the response capacity built around it disappears too, no matter how ready the crews themselves are to move. The redesign that followed didn't attempt to make every bridge immovable. It targeted the specific failure mode that caused the worst damage in 1995, decks separating entirely from their supports and falling.
Engineers jacketed piers in steel or reinforced concrete to improve confinement, strength, and ductility, allowing controlled deformation without sudden, brittle failure. They strengthened or replaced bearings, the components that let a bridge deck rest on its supports, while still allowing controlled movement. They lengthened the seating area where a girder rests on its pier, so a shift in position no longer means the girder slides completely free. And they added unseating prevention devices, restrainer cables, and mechanical stoppers engineered specifically to stop a deck from traveling far enough to leave its supports, even after the bearings beneath it have already failed.
Some of these retrofits are invisible from the road, wrapped inside a widened concrete pier. Others are visible if you know where to look. A thick steel collar wrapped around the base of a column, added decades after the original structure went up. Drivers pass over them every day without noticing anything has changed at all. Up close, an unseating prevention device looks almost unremarkable. Thick steel cable or a blunt concrete lug bolted to the pier cap, positioned exactly where a girder would need to travel to fall free. It does nothing on a normal day. Its entire purpose activates only in the seconds when everything else beneath it has already started to fail. The objective is not to guarantee that every bridge remains immediately open. It is to prevent complete unseating, preserve the route where possible, and make inspection and restoration faster. The final chapter shows the same layered principle at one critical site. Earthquake motion, tsunami exposure, power loss, equipment damage, and cooling demands arrived in sequence.
Chapter 7: Onagawa, the site where every layer had to work. Of every nuclear plant along Japan's northeast coast, Onagawa Nuclear Power Station sat closest to the epicenter of the March 11, 2011 earthquake. The plant experienced extreme shaking that exceeded parts of its own original seismic design basis. Then came the tsunami. What follows is not a claim that Onagawa emerged untouched. It's an account of what happens when several imperfect defenses have to overlap at exactly the same moment, and what it actually looks like when they do.
Decades earlier, Onagawa's operator had chosen to build the site well above sea level, near 14.8 meters, informed by historical tsunami records for the region, stretching back centuries. When the 2011 tsunami arrived, it reached roughly 13 meters at the plant. The elevation kept the main reactor and turbine buildings out of direct reach of the wave, but lower-lying areas near the shoreline still flooded through seawater intake structures that were never designed to stay dry. When the earthquake struck, all 3 reactors shut down automatically. Units 1 and 3 had been operating. Unit 2 was midway through a startup sequence and not yet critical.
4 of the plant's 5 off-site power lines failed. 1 line remained available to the site. Unit 1 lost its own connection to that remaining power entirely and switched over to emergency diesel generators. Units 2 and 3 stayed connected through it, keeping their off-site power intact throughout. 1 plant, 3 reactors, 3 different power situations in the same afternoon. By the early hours of the following morning, all 3 reactors had reached cold shutdown.
None of this happened without damage. Plant staff would later document 61 separate components that were damaged or had compromised function during the event. Among them, an electrical breaker fire at Unit 1 caused by the earthquake itself, and the loss of one of 2 cooling water trains at Unit 2 caused by flooding from the tsunami. A subsequent IAEA review found that despite the scale of the shaking, only a small number of those 61 items were damaged badly enough to take an entire system fully offline. No reactor core was damaged at any unit. Containment integrity held throughout, at a site sitting closer to the epicenter than any other nuclear plant on the coast.
This is not a story where one wall, one generator, or one design deficient explains the outcome by itself. No single layer performed perfectly. The outcome depended on enough independent layers remaining available so that one damaged component did not eliminate every remaining path to safe shutdown. It's elevation deciding whether the tsunami reached the reactor buildings at all. It's redundant off-site power deciding whether emergency generators were even required at every unit.
It's plant operators making decisions under conditions no drill can ever fully replicate. Every defensive layer covered in this documentary exists for the same underlying reason. No single one of them was ever designed to be enough on its own, wherever it happens to be installed. Onagawa shows that principle under one of the most severe compound events the site had ever faced. Extreme shaking, tsunami exposure, power loss, equipment damage, and the need to maintain cooling.
None of these 7 places survive because they're indestructible. Tokyo Station survives because the ground beneath it is allowed to move independently of the building sitting above it. Skytree survives because 2 structures inside one tower are built to deliberately disagree on how fast to sway. The Shinjuku Mitsui Building was retrofitted to control long-period motion more effectively than its original 1974 design. The Shinkansen turns a few seconds of physics into real braking distance. Tokyo Gas decides block by block exactly what to disconnect instead of shutting an entire city down at once. Bridge retrofits aim to prevent complete unseating and preserve the possibility of faster inspection, repair, and network restoration. And at Onagawa, elevation, redundant power, emergency systems, and human judgment all had to hold together within the same afternoon. None of these layers were ever built to make an earthquake survivable by themselves. Japan's real earthquake technology was never one wall, one damper, or one tower. It's the refusal to let a single failure become the only thing standing between a city and catastrophe. Because the ground will move again. The question was never whether something would fail.
It's how many layers stand between that failure and everyone still on the other side of it.